Imagine a complex, data-rich web application loading instantly. Instead of a standard 60 kilobyte JavaScript payload, the browser downloads exactly 8 kilobytes. That steep reduction in file size is not the result of a new compression algorithm. It comes from relocating where the application's code actually runs. To understand why this relocation is necessary, we have to look at the primary mechanical bottleneck of the modern single-page application, the hydration cost. When a traditional React application loads, the browser must download the entire JavaScript bundle, parse it, and attach event listeners to every node in the component tree. This process is called hydration. Hydration forces the user's device to spend CPU cycles running code just to make the page interactive, even if the content on the screen is purely static text and images. Shipping executable logic over the network to render read-only content wastes bandwidth and processing power. Fixing this requires a structural change to web architecture. Historically, the industry attempted to bypass this hydration bottleneck using server-side rendering, or SSR. SSR successfully accelerates the initial page load by executing React on the server and delivering a pre-rendered HTML shell directly to the browser. But SSR introduces a critical flaw, the all-or-nothing waterfall. The user sees the interface immediately, but they cannot click, scroll, or interact with any elements until the entire JavaScript bundle finishes downloading and the hydration phase completes. The server sent the HTML, but the network still had to transport the complete underlying component logic to make that HTML function. SSR improves the visual first paint, but it fails to reduce the actual computational workload placed on the client's device. React server components are the mechanical solution to this lingering hydration penalty. Unlike standard components, server components never execute in the browser. They remain entirely on the server, where they can query databases and access file systems directly without exposing secure credentials. And rather than compiling into raw HTML like SSR, server components output a highly specialized serialized data format representing the UI. This format allows React to build an interleaved component tree. Historically, the boundary between the server and the client sat vertically behind a JSON API. Server components rotate that boundary 90 degrees, slicing horizontally straight through the middle of the application's component hierarchy. The serialized output of the server nodes streams across the network and seamlessly merges with the interactive client nodes. Because the server nodes are fully processed before they leave the data center, the JavaScript code that authored them is never sent to the browser. By shifting the rendering phase ahead of the network boundary, React eliminates the hydration requirement for any static UI, cutting payload sizes down to practically zero. Of course, applications are rarely perfectly static. Moving logic to the server introduces the challenge of loading heavy asynchronous data without delaying the rest of the interface. React addresses this securely on the server using the suspense boundary. By wrapping a slow component in suspense, the lightweight outer layout of the application streams to the client's document object model immediately. While the user views the layout, the heavy dashboard component executes its complex logic and database queries safely behind the server boundary. Once that execution finishes, the resulting data grid streams down to the browser and injects itself into the established UI shell. In a standard single-page application, nested components often trigger cascading API requests from the browser, creating long data waterfalls. Server components eliminate those client-side waterfalls by handling the heaviest computational and asynchronous tasks in the environment best equipped for them, the server. When data fetching officially relocates to the server, the architectural definition of front-end state has to change. For the past decade, developers routinely stored remote API responses inside global client-side stores. That practice is now obsolete. This diagram shows a 4-quadrant mental model for state management, mapping exactly where specific types of data belong. Traditional API responses fall strictly into the server state quadrant. They should be managed by specialized caching tools like Tanstack Query, rather than pushed into the front-end application state. With server data properly isolated, the actual footprint of global client state shrinks dramatically. Libraries like Zustan or Redux are no longer needed to cache database records. They are reserved solely for tracking ephemeral user interactions, like toggling a dark mode theme or managing a multi-step modal. Adopting server components collapses the requirement for massive, monolithic state managers in the browser, leaving a much cleaner and simpler front-end architecture. These low-level mechanical efficiencies map directly to the high-level organizational challenges of large engineering teams. Enterprise software scales across two distinct axes, horizontally to manage multiple autonomous teams, and vertically to manage code execution. This schematic illustrates the micro frontend architecture. It provides horizontal decoupling, allowing independent teams to build and deploy discrete features that merge into a single top-level application. Server components facilitate this team autonomy by allowing developers to co-locate data fetching and business logic directly within the component on the server. Because the server-side logic is hidden behind the component boundary, one team can implement complex data requirements without conflicting with the global state or hydration strategies of another team. Mastering this boundary means that as the application's feature set grows, the cost to the user's device remains constant. An enterprise can add hundreds of server-rendered features while maintaining the performance of that initial 8 kilobyte baseline. By executing the bulk of their code before it ever reaches the network, engineers can build applications that are massively complex on the back end, yet remarkably lightweight for the end user.